was an update to my system, so it took a lot of time. Let me close all these windows. Remind me later. Okay. So just let me know if you guys are able to hear me. Not able to see any comments. Do we have someone? Hello? I do see 3 out of 11. Only 2 staff I'm able to see. I'm not able to see the other people. Can you guys just ping me on the chat window? Okay. I hope you guys are able to hear me. I'll start the session. So today it was kind of a doc-based session which has got requested for Flume and Uzi. So we will cover about what is Flume and what things we will do with Flume, and in the later part of the session we'll understand about Uzi. I hope you are comfortable with Hadoop and the architecture part. So Flume fits into the problem of data ingestion. So where data ingestion using weblog data or clickstream data or any machine related data, machine log data, and so on. So in this particular presentation, which will go through all the what is the problem and what is Flume and how is it answering the problem, and in the end we will do one practical to understand about how to run Flume. So the current situation is like you might have hundreds of servers running in different locations, which might generate a large amount of logs, which should be analyzed together, and you would need to have Hadoop based system to process them. But the problem is, how do you send all these log to that place where Hadoop is? And you really need a reliable, scalable, and an extensible solution which can manage all this stuff. So the solution to that would be some kind of process which could scale on the fly, and then whenever there are large number of logs getting generated, it could have more number of capacity, and then can go through transferring the data between whatever servers and the Hadoop based system. So the situation is something like this. So you have log data, and then you are moving the data to Hadoop. There comes Flume for our rescue. Okay, just a second. So there comes Flume for our rescue. So Apache Flume is a distributed data collection service that gets this flow of data which is getting generated in these weblog servers, or maybe your clickstream data, or data from Twitter, or any kind of fire hose, which is generating a large amount of data. So that large amounts of data gets generated and then gets passed to service something like Flume. And Flume is kind of one point repository to get this huge volumes of data, and then we'll pass it through Hadoop. So the problem solution is you have something in intermediate step called as a Flume agent. So you get all these log data getting funneled through this Flume agent, and this Flume agent can do this HDFS writes and then put the data into HDFS cluster. This is kind of a scenario where we are using a single Flume agent, but in real world scenarios we would not be using a single Flume agent, because we will be having a lot of server logs, and maybe connected to multiple servers, and you would like to fetch information from multiple servers and then feed it to a single HDFS output location. So what we will do is we will use a multiple Flume agent scenario where your weblogs get funneled into one or more Flume agents, and then output of that Flume agent would be fed to another Flume agent. So here, as we see, the output of the first set of Flume agents is not the HDFS, but it is another Flume agent, and the input of this Flume agent is not the logs, but it is the output of the previous Flume agents. So because there is a network transfer between the first Flume agent and the second Flume agent, we would also need to consider like how we would do an efficient network transfer, and in such scenarios we would either use a compressed serialized way of passing the data, and one of such serialized way of passing data is using Avro formats or Parquet format and so on. So when there is an inter-agent communication, we would use this kind of compressed format things so that your network latency can be reduced. So in this scenario where you are seeing this weblog server could be any of your JBoss server, or it may be a Tomcat server, or WebLogic server, where it's kind of generating logs, and then that logs get fed into the Flume agent that goes to another Flume agent, and then finally that Flume agent will split the data into HDFS. Important thing is to understand about what are the components of Flume. So the components of Flume are something like this. So all this agent what we are talking right now is kind of consists of these three important components. One is the source, second one is channel, and third one is sink. The source, as the name suggests, it is kind of a starting point. So it is the one which is connected to this web server logs, or your clickstream logs, or your Twitter feed, or your Facebook API, or WhatsApp API, or any of the internal API, or any of your edge nodes of a IoT devices. So IoT devices are this Internet of Things where you have this a lot of data getting funneled and coming into this edge nodes, and that edge nodes would be feeding the data to your Flume agent. So your web server and all these other things which I was talking about are called as clients. And every occurrence of whatever this client does is called as an event. Whenever an event occurs, that the data goes to the source, and source is the one which is getting configured to understand what is the input and where it has to put the data. Generally, the source puts the data into something called as a channel. Why do we use channel is because imagine this is like a water flow through, and you are having this huge pipe which is connected from the inlet to the outlet, and the reason we are using this huge pipe is because we can do the buffering of this flow of water, so that it doesn't get rushed through the complete pipe. And whenever there is a data flow, because there is one problem that the sink is the final one which is getting connected to the HDFS node. And the problem is, like, if I can directly send the data from a source to sink, which I can definitely do, in replacing the channel, but the problem is the speed at which the data which is generated at the source is not equivalent to the speed at which the sink is writing into HDFS. So because this is some kind of network required and an I/O required, because the data is written into a physical disk, there will be some issues or slowness in the way the sink writes into HDFS. So because there is a huge amount of data which is getting generated near the source, and it cannot write at the same pace, and it cannot match, the sink cannot match the source, we feed the data into something called as a channel. We will understand like how are the different channels are, how are different types of channels, and what are sinks and what are sources. But just this gives us a raw idea about how is this looking like. Okay, I hope you're following the session because I don't get any feedback here. Okay, so let us go forward and understand each and every component in much more detail. So the components which we have looked at as the event, client, and agent. So the agent is the one which is containing sources, channels, and sink. If you take a component called a source, it is the one which is getting all these logs. So it's basically getting the sys logs or netcats or any Unix-based logs or Linux-based logs or Windows-based logs or any such kind of logs getting generated. If at all it is a agent-to-agent communication or in a case of multi-agent communication, you either use a Avro or Thrift or Parquet kind of formats so that you would use the serialization concept so that you reduce the uh, amount of network bandwidth which is utilized for transferring the data. Next one is the channel. So the channel, as I was saying, it's kind of an intermediate buffer layer between your source and sink, and it is used for this kind of buffering the data which is flown through the source and then slowly sending it to sink. The different types of memory channels are memory, file, and database. So if at all I want to use this fastest kind of transfer between your source and sink, then I would use something called kind of memory based channels, because your data is always persistent. Your persistence in the RAM, and because the data is available in the RAM, you can directly query that and then get the data very quickly. But when the amount of read-write capacity is not that important, what we can do is we can either do a file-based thing or a database-based thing. File-based thing is simply like you're writing up a log of data in a file, and then once the data is moved out, you delete that file. Whereas in the database, it could be a physical database, either it could be a relational or an NoSQL database, where you physically store the data in that database, and then you take care about purging the records as once they are consumed by the sink. So how do we implement those all things? That is dependent on the Flume's architecture. So we are not going very deep into that architecture part. Whenever we are using Flume, because we don't do a lot of architectural based development, we just need to understand the tool and how to use it. So that is what we are concentrating on. See, these channels are very importantly to understand is that they are fully transactional, so that whatever comes in goes out. It is nothing like lost in the woods kind of scenario. Right? It is whatever comes in completely goes out. The component that takes the events from the channel are the one which is called as sink. So sink is basically the end of the Flume agent. So it is a kind of connecting either to a HDFS or HBase or Hive-based things, so that once you get the data, you then dump the data into this final store, which is either HDFS or HBase. In case of a agent-to-agent communication, then you could output a Avro-based data, because in an agent-to-agent communication, the intermediate agent will be sending the data to another agent instead of a HDFS or HBase. So that's the reason you would be doing that. So up for the components, let us do a quick demo on that. Let me open up. Okay, I have to open up a. So I use Cloudera's VM. So I hope by this time you are familiar with VM what I'm using. So it might take a couple of seconds for booting up the virtual machine. So I'm using VMware Workstation 12, and this is CDH 5.5. So the example what I have is kind of a log generator, which is simulating the log generation of either a Windows machine or a Linux machine or any other web server. So it generates log in a very so we have written a Python program which can generate this log continuously, and that log is getting tailed by a by one program, and then it can output that log onto the console. So we will see all the steps together, and then we'll understand like how this log generator generates log continuously, and then we will configure the agent 1 and agent 2, which are like we will be doing a multi-agent scenario where agent 1 is taking the data from the log and then putting onto the agent 2. The agent 2 takes the data which is output from the agent 1 and then puts the data into HDFS. So we will configure the agent 1, agent 2, from input till output, and the output would be again on HDFS. So we'll see the configuration files, we'll see where we have to put those configuration files, and what are the commands to execute this Flume agents. We will see all those things, and then once that is done, once we are clear, we will go to the next Uzi part. So just give me a second. So once this boots up, we will be able to see it completely. So just let me hide the, for a second. I'll be doing it. Just a second. Checking that whether this is done. It's still booting up, almost there, because it will take a few minutes for booting up. If you are aware that because it back in the back end, I can show you. If I do an Alt tab, then I can show you that it is booting up all these servers. So the machine itself will boot all the servers and then show things. So once it boots up all those things, it's almost done. It has completed booting. It is starting up the machine. So once it starts up, I'll show like simple Flume-based code. We will see the Flume-based agents, and then we will see like how to configure them. Okay, so it's done. Let me start. I go to the places and home folder. So I have a couple of files stored here, and I kind of have a directory path in which I store files. So I have something called as code and data. and within that there is something called as code, and then something called as Flume Basics. So this Flume Basics has this Flume exercise text. Let me show that what it has. So what this explains is from a ground up configuration of Flume. But if you are running any of the Cloudera or Hortonworks or MapR based these things, you would certainly do not need to install it. If you are installing, if you have installed Hadoop as a standalone thing, then you would certainly need these steps. So basically you need to do sudo yum install flume-ng, and then you do some of the configuration related parameters. Okay, so I'll show you. First what we'll do is open up a terminal and then navigate it to the Flume Basics path. So I'm in there, and we will less command would be opening up those files. So instead of opening within the command line, we would directly go and open it from the folder. Just a second. So we will open up the Flume Agent 1 and Flume Agent 2. This is the Flume Agent 1 and then Flume Agent 2. So if we see, the Flume Agent 1 is something which is talking to the one which I was telling that I will generate a log data, and so it will have something called as source, channel, and sink. The source is something which is connected to this log data, and then that data would go into the channel. So here we are using 1000 event buffer. That means that 1000 occurrences of this particular thing is the capacity of this memory buffer. So imagine like one event is taking 1 byte, then it is like 1000 bytes. If one event takes like a couple of bytes, then those number of bytes of data. And then finally, because it is agent 1, what we are trying to do is we will put the data into Avro. So that's the reason we select the sync type as Avro, and this Avro is hosted on the Cloudera machine itself, so that we don't have to install it separately. So it is running on localhost 5555 support number. So once the agent 1 is complete, that sends the data to Avro, and then Flume agent 2 basically picks up from the Avro file. So agent 2 also have source, channel, and sink with a different name, agent 2, and then it picks up the data from Avro, and then again it also uses 1000 event memory buffer, and then finally it puts the data into something called as HDF. So in HDFS and in something called as Flume folder. So it is important for us to understand whether a Flume folder is existing or not. So let me check. Let me check if we have Hadoop file system hyphen rest. I hope it is not there. Okay, it is there. So what we have to do is we have to delete that. Let me make it a bigger screen. So the Flume is already there. Then what I will do is Hadoop file system hyphen rm hyphen r. No. Okay, it is deleted. Let me clear it off. The reason I deleted is because this new program will generate a new folder out of it. So let us see the log generator.py, which is a Python program. So there are the intent of this log generator program is basically to randomly generate a string which is similarly like a error log. So it randomly picks up a URL. So there are a bunch of URLs available here. So it randomly picks one URL, for example, Cloudera, Facebook, and then Twitter, Amazon, and so on. And then it picks up a random path like index.html, contact.html, about.html, and so on. It randomly picks up an error code. It could be 404, 505, 500, and so on. So these are some of the error codes which we are putting to it. And it randomly generates an IP address. So the IP address is of range of 1 to 255, so it is like 192.168 kind of something, whatever is our IP address. So basically this random function, what it does is from a given selected range, it will try to pick up a number randomly, and then it gets like four numbers, and then once we add them or concatenate them as a strings, then it would be like a real IP address with a dot in between. So 192.158.122.61 kind of thing. So once all these things are done, what we do is we run a method which is like an infinite loop. So we run a while true. So when we are saying while true, that means that it is continuously running, and then it takes a break for 5 seconds. Every 5 seconds it goes into the sleep mode, and then once it wakes up, it basically builds up this, it calls these methods, so the ones which we have kind of created. These methods would randomly return some web address, and then some path and URL and so on. So finally it will create a line which is something like this: HTTP, and then HTTP address, and then URL, the path, and then IP address. And then it writes that line onto the log file. So this is how it looks like. So what we will do first is we will go into this and run that file. Before that, we also have to do a little steps. So we have to copy the properties files into the Hadoop configure folder. So copying that. So the configuration conf folder is from I will be executing the Flume agent. So once this is done, what we can do is let's open this up. We can create a directory, the one which I've deleted right now. Create a directory. So once that is created, we can navigate. We can run the log generator.py. So you can simply use Python log generator.py directly. Python log generator.py. So it is generating these logs. As you see, it is running. My Python program is running. It is generating every 5 seconds. It takes a break and then generates it again. So giga home and kind of stuff. So we can leave that particular thing as it is and go to a separate terminal and then run the downstream agent, which is Flume agent 2. Okay, open up another thing and then paste it. So this is the command in which the way we have to write. So we have to write flume-ng, the agent, and then we give kind of what is the configuration folder from where we are picking up the file. We can also specify a config file name. What is the file name which we are trying to do, which is flumeagent2.properties. And you can give a generic name to it. So you can say it is agent 2. So what this will do is, like, the downstream agent is started. So the agent 2 is started. So once the agent 2 is started, then after this we have to start the agent 1. So as and when the agent 1 is ready, it would pump up the data to agent 2, and agent 2 would be writing the data into HDFS. Okay. So it just started up, and open up another terminal, and then we will run the agent 1. Agent 1 command also is the same, no change, except now we are running the agent 1 command. So let us see if this one, agent 2, started. Okay, once that is started, you would paste it. I have not copied it. Agent 1. paste it. As this basically starts, then we can open up another terminal to quickly see how the data is created. So if I do Hadoop fs-ls flume, that's where my data is getting created. So if I just do that, as you see, there is a lot of data which got generated. This is generated today only, 2016, 23rd, and roughly about 800 bytes of individual file is getting generated. So as we run so many of them, you would be generating so much of data. So this, as you see, this log is continuously generated. So likewise, so this is kind of a simulation to tell like how the data gets generated. Imagine this is a real web server log which is continuously generating data. You can feed that into your Flume, and then Flume will internally feed the data into HDFS. So once you get the data into HDFS, now you can do a lot of stuff. Right? So you can do analysis on this data, identify how many 404s are there, or for a given time period for this particular arc, how many 404s are there, how many 500s are there, and so on. Like that, you can do analysis. Because it is a randomly generated subset, you would be getting almost equal data. But when we get a real data, you would be getting a lot of stuff. Okay, so let us go back. Okay. To close this, because it is a continuous log, you have to first go to this and press a Control C, which will basically kill the module. Likewise, you can go to all of the modules and say Control C, which will basically kill all of the modules. And so do a Control C, which will kill this one. Likewise. So it has basically executed, and it has moved the logs to this particular folder, the Flume folder. And if you wanted to see the properties again, in the final thing we have kind of put a prefix to flume.log. So that's the reason we are getting this kind of data. Where is it? This one. So within the Flume folder, we are getting it with the prefix flume.log and then with the timestamp. This is the timestamp field. It likewise, you can get a lot of data into Flume, and then you can analyze it with your regular MapReduce or Pig or Hive and other programs. So next, what I will show, okay, we will go through Uzi. So this is what is Uzi. Let me open up my full screen mode. Okay. So Uzi is basically a workflow scheduler. So this is something like for scheduling your jobs. So once we are done learning MapReduce, Pig and Hive and so on, the other part which is left over is, how do I schedule these jobs in such a way that, once a job is completed, some other job is automatically triggered. So this is something like an automation. So you do not want to manually intervene and wake up in the middle of the night and then go and check whether the job is done or not. If yes, then start up the next one. So you don't want to manually intervene in that. So you end up writing some scripts which would run and then kind of execute on the fly. So it's kind of a workflow scheduler for Hadoop, and it was designed by Yahoo because it has a lot of complex search things. But now Yahoo is almost down. There are very good projects. Hadoop was invented at the Yahoo, and then many of these ecosystem tools like Pig and Oozy, all those things were invented at Yahoo. Okay. So Oozy allows a user to create directed acyclic graphs of workflows. So what that means is, like, once a MapReduce job is completed, you will start a Pig job, and once the Pig job is completed, you will write a Hive script, and Hive script sends the result into something else. So it's kind of a directed and acyclic, and there are no cycles in that particular steps. So that kind of jobs you can schedule with Oozy. Oozy can also run plain old Java programs called as POJOs and Pig workflows, and it can also do interactions with HDFS. That means that you can interact with HDFS, create folders, create directories, delete files, move files, copy files. So all these nitty-gritty details of dealing with HDFS can also be done with Oozy. Oozy can run jobs sequentially or in parallelly. So that means that sequentially can happen like one after the other. After A, B happens, after B, C happens, and after C and D happens. So this is the sequential steps. Parallel instance where you wanted to parallelly run couple of scripts, and then output of all the scripts come and join at a different place. So we'll understand about something called as fork and join in the coming slides, which will help us doing this parallel operation. So the best way of doing jobs simpler is to just cascade things. If you do not have an Oozy thing, what you can do is you can just cascade things and you are done. But the major flexibility whatever it gives is, like, it will give the flexibility to start, stop, and suspend and rerun the jobs as and when you want. And you can also start the jobs from the step of failure. So if at all you're doing a mega multi-terabyte data scan and you're doing some analysis, you have completed certain part of data and you also done some analysis and the results are also there. You do not want to rerun all the steps starting from zero, right? Like you have done a lot of steps, so you only wanted to start from the point where it failed. So that kind of capabilities are available with Oozy, and if you are doing manually, that those kind of things are very difficult. You have to write a lot of program for doing that. So Oozy allows you to restart from the failure. So the one which I was saying was, you failed at certain point in time, you did a lot of transactions before that, so you can directly restart from the point of failure. The other features are, it has a Java client API, and it also have this, it can run periodic jobs, and it can also receive emails and do some arguments. So how do you make a workflow is, it's basically like, for example, if you want to do it for a MapReduce based job, you would write all the information in something called as workflow.xml. So workflow.xml is kind of a plain old XML file which has certain parameters, and for those parameters you would specify the data. And how do you make this workflow is, you can write all these parameters in the flow, and you can also do something called as, like, a file called as job.properties file, which is kind of a shortcut key for your workflow. And all the major links like name node, job tracker, and input path, output path, and all these things which are kind of repeated in the workflow could be kept in the job.properties file. In that data, you can use it for the execution. I'll show some examples to show you like how the job executes. So these are the couple of start, end, and error nodes. So start node, as the name suggests, it is the one which is starting the Oozy workflow. End node is the one which is ending the Oozy workflow, and error node is something, if any certain error happens, it would go to this particular error node. You can customize the error nodes depending on the type of error you get. If at all you're getting a MapReduce error, you go to the MapReduce error node. You can if you're getting a Pig error, it goes to a Pig error node. There are two important things here. The first one is the action node and the control node. So action node is something which is basically running the real core of the OZ. That means that it runs the real MapReduce jobs, big Java class, or something of that sort. So it has something like OK and error. So if it is within that action node, if it's saying OK, then if that is successful, it goes to the OK node. If it is having some problem, it will go to the error node. So this is an example of a MapReduce action node. So in this MapReduce action node, simply we are giving like what is the job tracker address name node and some Hadoop related configurations. If this node completes, if it is successful, it will go to the OK node, which is the next step. And if it is having some issue, it will go to the error node. Like that, you can cascade. After this MapReduce, this OK step goes to Epic node, and that goes to some other node, something like that. So it is you can create kind of a cascading effect. Who's a Java job tag? So this is an example for a Java thing. So as you are saying, within the Java tags, you have this information. So you can also give job tracker name node and all other Java related parameters. If at all you are creating like a giving a class path and giving all the arguments for execution, you can give all those things. And if it is successful, it goes to the OK node. If it is having issues, it goes to the error node. USI file system tags are basically for doing any file system related operations like delete, make directory, move, or change permissions, and then copy to a particular directory and so on. So all this kind of file system related operations you can do within file system action node. Apart from the major workflows, you can also have something called as sub workflows, which are like child workflows within a workflow. So as a parent workflow is running, and under the parent workflow, they will write a child workflow. Once that is done, it will come back to the parent workflow, and then process follows. So that is something what we call as a child workflow or sub workflow. The thing I'm talking about parallelism is where you would use something called as fork and joins. So fork is the place where parallelism starts. So it starts these parallel jobs. It's kind of splits the process into two paths, and then both paths are executed, and then they join at the join node. So fork and join are very popularly used in other kind of contexts also, where we are doing the splitting and doing a parallel operations. So it's kind of a same thing. We can also do decision nodes. So decision nodes are something like you have a switch case conditions. So these switch case conditions are basically like, so if certain thing happen, then do this. If your size of this file is greater than certain GB, then only execute. So such kind of conditions could be used. We can also use like Hadoop based counters to say that if the file records after so and so, then you can execute the file and so on. So that kind of operations could be done. OZ parameterization, we've just touched base upon it, telling about job.properties files. As I said, then it is kind of a shortcut key to the actual files which are mentioned in the workflow. So all those files, for example, like job tracker, name nodes, input path, output path, table names, and so on, can be used as a constants and within your file system. So how do we do that is, with this example, as you're seeing, you would say that within a curly braces and with a dollar symbol, you would say that it is a job tracker, and this actual information of the job tracker would be kept in your job.properties files. Likewise, if at all you have an input directory, you can give that input directory. If you have an output directory, you can give that output directory. Just with the simple name, but the bigger path is kept in the job.properties file. So rerunning a failed job is like a piece of cake in OZ, because you can simply say while running the command whether you would like to rerun the job or not. And if you would like to skip cut particular nodes, and if you want to rerun from a specific node, These kind of things are also possible. You can define these kind of properties in the job.properties files whenever you want to run your job. There are other very much deeper topics which we will not be covering in this, because this is kind of an introduction to UZI. We were not doing a complete UZI based training. So certain things we have are called as we have seen about workflows and job.properties, but we also have something called as bundles, and we also have something called as a coordinators. So it's something like this. UZI by base, we will have all the workflows, and the workflows will be combined under a bundle, and all the bundles get combined under a coordinator. So this is how those kind of things work. And then a couple of notes telling like how the things work, and then kind of an example to show like how this flow looks like. So it's kind of starts with a start node, it goes to a fork node, and this fork node kind of divides the path into two different paths, and then it executes a couple of jobs. The ones which are in purple are MapReduce jobs, so it executes the MapReduce jobs and that does the join. And then it goes to this blue color Java job doing something called as extract URL matching kind of thing, and then finally extracts the offsets. This is how it looks like. Okay, a couple of links are there. So this is more about the UZI. So I think we have covered a very decent understanding about Flume, and did an exercise on Flume. UZI is more or less like a theoretical concept. So we will just understand what is UZI, how it is used, and so on. There is not much a lot of practical stuff on that. We'll just understand the theory behind it and just close it. Okay, so I just wanted to check if you have any questions on this particular thing, or else we would close the webinar. So there's some kind of thing I'm not able to see the comments from the person, but I hope the session was fruitful. You had information about Flume and UZI, and I hope that was interesting. So thanks for attending it. I'll be closing the session in a minute. Okay, thank you very much. Bye.